The headline says, Catl will mass-produce sodium-ion batteries by 2026 with a target range of 600 kilometers. It sounds like another battery upgrade, but it signals something far more fundamental than just capacity gains. This milestone marks the moment where energy density ceases to be the sole determinant of electric vehicle success. For years, we have operated under a strict dogma: lithium is king because it stores the most energy per kilogram. If you could not achieve high range with lithium, you were stuck in low-end vehicles or short commutes. But as Catl moves toward this 2026 production target, they are proving that for mass market adoption, supply chain security and cold weather resilience matter more than absolute density. We are witnessing the end of the lithium-only era for city and mid-range transport. To understand why this shift is happening, we must look past the marketing numbers and examine the engineering constraints that have actually dictated battery development over the last decade. The prevailing narrative has focused entirely on maximizing energy density to squeeze more miles out of every kilogram of pack weight. This obsession drove an arms race in materials science where engineers chased higher nickel content and thinner separators. However, this approach created a fragile foundation built on volatile raw material markets. Lithium, nickel, and graphite are not infinite resources with stable supply chains. Their prices fluctuate wildly based on geopolitical tensions and mining bottlenecks. When production scales up to meet global demand, the cost of these materials becomes unpredictable, creating a ceiling for how fast manufacturers can actually build vehicles regardless of their engineering capabilities. Recent techno-economic modeling confirms that sodium-ion batteries achieve competitiveness not merely through raw material costs, but by eliminating this pricing volatility entirely. Sodium is abundant and ubiquitous in nature, found in common salt. This abundance removes the scarcity premium that has plagued lithium markets. By shifting to a chemistry based on materials we can source reliably anywhere on Earth, engineers are solving the supply chain problem at its root. The 2026 milestone from Catl represents a strategic pivot where this security is valued higher than squeezing out an extra 5% of range density. It acknowledges that a car cannot be sold if you do not have enough battery cells to build it in the first place. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This shift also addresses a critical performance gap that lithium-ion chemistry struggles with: extreme cold. In traditional liquid electrolyte systems, low temperatures cause ions to move sluggishly and can lead to plating issues where metal deposits on the anode instead of intercalating smoothly. This degradation reduces range significantly in winter and accelerates long-term battery wear. Sodium-ion batteries possess intrinsic thermal properties that allow them to perform far better in freezing conditions without requiring as much external heating infrastructure. Emerging solid-state technologies, including anti-perovskite and sulfide electrolytes, are further resolving historical safety and conductivity limitations. These advancements mean the battery does not just survive winter, it maintains performance when lithium systems often degrade or require inefficient thermal management to function safely. Consequently, this technology necessitates a fundamental shift in how we design vehicles at the system level. The transition requires engineers to abandon lithium-centric designs for battery management systems and thermal architectures that were optimized solely for maximizing density. Instead of fighting cold with energy-hungry heaters, new sodium-ion systems can utilize their superior low-temperature performance as a baseline feature. This changes the vehicle's weight budget and packaging constraints significantly. For city vehicles and mid-range cars where daily travel distances are predictable but weather conditions vary wildly, this reliability is an engineering win that outweighs absolute range potential. The 600-kilometer target mentioned in recent announcements does not imply sodium-ion beats lithium on every single metric. Rather, it signals a specific design envelope where the trade-offs favor stability over maximum density. The reality of energy density remains a constraint for long-haul dominance. Current sodium-ion variants still store less energy per unit volume than optimized lithium systems designed for high-performance applications. This necessitates a trade-off in vehicle weight and physical size if manufacturers were to attempt ranges beyond standard urban commutes without massive pack expansions. However, this limitation is not a failure of the technology, but a definition of its ideal application. The victory for sodium-ion is specific. It dominates the segments where supply chain reliability and thermal performance are the primary engineering constraints rather than raw energy storage capacity. We are moving from a world where we chase density above all else to one where system robustness dictates the winner. This change in perspective reshapes the entire narrative of electric vehicle adoption. For years, critics argued that without ultra-high-range batteries, EVs would never truly replace internal combustion engines for the average consumer. The Catl 2026 production plan suggests a different path. Rather than trying to force every battery into a high-density mold, we are finally engineering vehicles around materials that work reliably in all conditions and can be produced at scale without resource bottlenecks. This approach allows manufacturers to build more cars faster because they are not waiting for scarce minerals or fighting against the physics of freezing temperatures. The lithium-only dogma fails to account for these broader systemic realities, treating energy density as a universal solution when it is only one part of a complex engineering equation. As we move toward 2026 and beyond, the focus will shift from chasing theoretical maximum ranges to validating real-world deployment stability. The integration of solid-state sodium technologies promises superior cycling stability over time, though specific timelines for achieving necessary interface optimization at scale remain dependent on continued R&D intensity. Yet even without perfecting every edge case today, the core advantage is already clear. A battery that works in the cold and can be built tomorrow because the materials are available everywhere. This is the engineering story behind the headlines. It is not just about better chemistry. It is about building an infrastructure where energy storage scales reliably enough to support global electrification without hitting material walls. The 2026 milestone signals a paradigm shift where supply chain security and cold weather reliability supersede energy density as the primary engineering constraint for mass-market EVs, effectively ending the lithium-only dogma for city and mid-range vehicles. Techno-economic modeling indicates that sodium-ion batteries achieve competitiveness not merely through raw material cost, but by eliminating the pricing volatility of lithium graphite and nickel markets that plague production scaling. This transition necessitates a fundamental shift in battery management system algorithms and thermal architecture as engineers must abandon lithium-centric design patterns to fully utilize these new capabilities. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.